How you doing? This is the second part of chapter 4 in volume 3, and we're talking about instrumentation. And when we talk about conductivity, we're talking about conductivity is the measurement, and this is on page 289. Conductivity is the measurement of how well a substance conveys an electrical current. And the most common conductor used to power electrical devices is copper wire. So conductivity, we're measuring the aqueous solution in an indirect measure of its ionic strength. So we're using a electrical current, and we're measuring the ionic strength, and that will give us an idea of how much TDS is in the water. So a TDS sample that we take, that may take up to 24 to 36 hours to get the results. This is in time results that we can get, and so we can use that for a variety of measures. I know at like my wastewater plant, we measure the DI water that we're using in the lab, and so we want to make sure that it's low in conductivity. I know on the water side or wastewater side, if you are um, operate an RO plant, you will measure the conductivity after the final product to see if you are truly eliminating TDS um, in your effluent. Once again, proper calibration maintenance. They could be subject to fouling, biofouling, or scaling. Read your manufacturing equipment for all that. But as with all sensors are, sensitive to temperature, heat, calibration. So we want to make sure all our sensors are calibrated. On page 299, conductivity can be used to estimate the total dissolved solids concentration of solution. Once again, TDS is normally quantified by filtering a well-mixed sample through a glass filter and evaporating the filtrate. So as I alluded to before, we don't have to do this method, that we can kind of speed that up with a conductivity meter. There on page 298, there are some instrument and control of conductivity meters that you can see. So gas flow, we also measure gas flow, whether you're in a plant that has anaerobic digester or you have an aerobic tank. We use some sort of gas flow or airflow monitoring thing, equipment, to see how much CFMs that are going to our tank. So thermal mass flow meters are dominant in the technology in wastewater. They require little maintenance and they produce accurate and repeatable results. Page 303. Thermal mass flow meters on 304 consist of two resistive temperature device elements constructed, one from platinum or stainless steel. One of the elements is passive and measures the temperature of the ambient conditions to serve as a reference. The other element is actively heated to a known temperature and is the source of the heat transferred from the flowing gas. So that's the makeup of a thermal gas meter. It can be an insertion type probe or it can be mounted in a spool piece. And so you can see on page 306 in an insertion type um, thermal gas meter. When we talk about dissolved oxygen wastewater treatment, it's super important. Uh, just this week we were measuring oxygen in one of the aeration tanks, and one of the blowers weren't kicking on, and so having that data come back to the SCADA, especially right now where we're at, it's super hot, and having that data come back and knowing what the oxygen level is in your tank is paramount, because if you're not getting the correct oxygen, if you have over aeration, you can have problems in your clarifier. But if you're doing under aeration, you're not really getting rid of the ammonia and the carbaceous BOD. So, we have DO probes out into the system, and on page 312, you can see some of the aerators that normally are in a um, a wastewater treatment plant. Maybe you have one of those, but measuring DO, uh, you know, by volume, atmospheric air contains 78% nitrogen and 20% oxygen. So when we're measuring those, we need to keep those concentrations in line. But there are a lot of variables that affect DO. In 316, variables such as temperature, salinity, pressure, all those account for it. And so when we calibrate our meter, the meter will take into consideration some of those, or we'll have to enter in the salinity of the water that we're testing. And, in the old days, we would do a Winkler test to measure the oxygen and compare it to the meter. But we also need to take in the barometric pressure, because as it changes, that's going to have effect on DO. Really, in the water and wastewater industry, we have two types of probes. We have the electrical mechanical sensors, and that was are constructed with a canode and an anode. And on page 320, a semi-permeable membrane isolates the electrodes and electrolyte from the sample being analyzed, while allowing oxygen molecules to diffuse in the measurement cells. So that measures DO by electrical mechanical means. We now have optical probes, which is sensing the dye. You can see on page 322. So as that dye luminesce gets luminate more or less, that tells you kind of how much oxygen you have. We use those in our aeration tanks at work, just to keep measuring. And you'll have field probes that you can take out that are portable. And you have probes that are what we call tabletop probes. And those are your base DO probes. It's important to know what kind of probe you have and the calibration methods used. So a lot of times, you want in the old days we would warm it up. So we would turn it on for 15 minutes and let it set in a BOD bottle that was saturated to get saturation. Every morning we flick the moisture off the tip of the DO probe, because all that will affect the calibration of your DO probe. So you want to look at the qualifications or the recommendations that they require. On page 325, you can see a battery operated portable dissolved oxygen. And then there's your tabletop base on 326. Gas meters, we deal with a lot of gases. We have the portable gas meters. You might need to bump test those, or annually test those, or every 6 months test those, because we're using those sensors to go down into tanks, faults, pits. And so you want to be able to calibrate those, and make sure that the audible and the visual indicators are working for the safety of people. Maybe maybe you have a chlorine gas room, and you have a fixed gas meter there. And once again, making sure those work and calibrating those. Normally, a manufacturer will send a bottle with a predetermined gas mixture to test those, and kind of do a bump test or a sniff test on that meter, so making sure that it operates correctly. As water and wastewater operators, we want to not get lax in the fact that we're going down to in a pit, but we want to make sure that we're protective for all. Hydrogen sulfide is a toxic, corrosive, flammable gas that's biologically generated in anaerobic bacteria. Once again, when we go down into lift stations, we want to know what's down in there. And so, by having a properly calibrated gas meter, it's paramount to what we do. On page 336, I'll highlight units for safety purposes generate an alarm notification when hydrogen sulfide concentration exceeds 10 parts per million, which is the permissible exposure limit. For the test, you need to know, the different levels there on the concentrations of the odor thresholds, and then, obviously, at 1,000 parts per minute, you'll death is imminent in minutes. Um, Oxygen concentrations, we need to know on page 339, there's a guy going down there and we're pumping fresh air into that. But, are we deficient or oxygen rich, so you need to know those numbers of 19.5 to 23.5. Because if it's oxygen rich, you could have an explosion in your manhole. If you're oxygen deficient, then when you go down into your manhole, you could collapse from lack of oxygen. We talk about ultraviolet light. We use that on page 342. And we use that to disinfect the water. And we just need to know how it works. Normally, we have a power supply, a DCA, which talk to your LCAs, which controls your lamps. It'll turn up or turn down if the lamp and the bulb that is actually in the quartz, the lamp that we talk about, and that intensity of that light is what's going to disinfect your water. You know, all that as we I'm sure I just bought a new car, and as technology gets advanced, we have more sensors, more ways to save energy. But with that, as water and wastewater operators, we need to really be aware of how to calibrate and to know when things are wrong. Sometimes you have to bypass a sensor. I don't recommend that, but sometimes you do to have to troubleshoot. But it's always imperative that we go back and replace that sensor, so when the next person comes, they're not having to re troubleshoot that sensor. Um, Keep going. Chlorine disinfection. We use chlorine disinfection, uh, and then we also use some sort of dechlor. And then with that, you're going to have some sort of pumping strategy or pumping mechanism, and then hopefully you have some sort of monitoring um, feedback that's coming back to your SCADA. So on page 354, you're on a dosing controller, and so it's going to tell as the flow increases or the organic matter increases, it's going to speed up the chlorine pump or slow it down. You don't want to pump 1 gallon of chlorine for 1,000 gallons and then do 5 gallons for the same 1,000 gallons. So you want it to um, modulate with the flow. As the flow increases, you want the chlorine to increase proportionally. And so you'll have some sort of controller and chlorine residue measurement system on page 357. I know, on 361, those are some types of either amperometric chlorine measurements or colorimetric. So, you know, amperometric instruments have free and total chlorine sensors, have a measurement cell, contain two electrodes submerged in an electrolyte solution. The electrodes is retained in the measurement cell by replaced a membrane cap that has a selective permeable surface. And an analyte is diffused through the membrane, and the electric current is proportional to its concentration is generated between the anode and the cathode. So that's your kind of your amperometric. Colorimetric, I believe, is more of a color. So your Hawk test, it generates like an intensity color, where the amperometric, under my understanding, is more of a electrical mechanical reaction. So your DPT reagents, you add the two reagents. I'm sure you've done it at a water plant, and your vial will become pink, and the intensity of pink is how much chlorine that you will have in there. Talk a little bit about ORP. So on page 363, ORP is measuring the oxidant reduction potential of wastewater at various stages of the treatment. Is important process. The ORP is a measure of the oxidizing and reducing strength of the wastewater based on its capacity to gain or lose electrons. So I worked in an RO plant, and we had an ORP, and if there was any kind of oxidant, potassium permanganate or chlorine that would foul the membranes before the water would hit the membranes, that ORP number would skyrocket, and it would shut down the plant so that we would not put any oxidants on the membranes itself. And so ORP is um, important. All ORP sensors are potentiometric cells with a chemically inert platinum measurement electrode and reference electrode. A lot of our equipment that we have is we use some sort of measurement electrode and a reference uh, electrode and some sort of solution or semi-permeable or permeable membrane, which you can see on 367. Um, Keep going. Compressed air. You may use compressed air to control valves. There's some advantages of that is that there's not electrical current. And I've worked at facilities that have those. You need to know that you have the different type of compressors that you can see. A multi-stage reciprocating one is on page 376. And moisture removal. I working with any kind of compressed air. Moisture condenses as the air temperature decreases following compression, and then condensation that accumulates in the air storage is usually expelled by periodic operation of the automatic drain valve. So, we need to make sure that if we do have compressed air, that we're getting rid of that water that's in the uh, in the tank. We talk about turbidity and suspended solids. When we talk about turbidity and suspended solids, we can use NTU, a neutrophilic turbidity meter. You know, um, a water sample with low turbidity will transmit light in nearly straight path since there are fewer particles in the solution to scatter it. So on page 411 or on page 383, you can see kind of how that works. A turbidimeter emits light, and the degree of light is scattered into proportion of the turbidity. So if the sample was more turbid, that light is going to scatter more. And so we can kind of use that to measure turbidity in our water. So if you're operating a surface water or a wastewater treatment plant, having a turbidity meter, especially if you're not there, can tell you how well your clarifiers are working or your pre-treatment before you're um, discharged to the river. So that's really it on instrumentation. I hope you enjoyed it, and I will post this to the line. Thank you.